And welcome back, folks. So, last video, we had our quick review of eigenvalues and eigenvectors, right? Stuff that you should remember, maybe a few things that were familiar, and a couple things that might not have been. But now we remember how they work. And what we would like to do in this video is remind ourselves of some important facts that we're going to be invoking as we move forward, involving eigenvalues and eigenvectors for matrices. So, some things that you're going to have to recall. Let's go ahead and dive right in. As a proposition, if you have a square matrix with a zero eigenvalue, right? If zero is an eigenvalue for your square matrix, then it doesn't have an inverse, right? This inverse cannot exist. So, what the quick proof for this would be that if you did have a zero eigenvalue, then A times V would have to be zero for some non-trivial solution, right? So being an eigenvector associated with lambda equals 0 means that you are actually part of a non-trivial kernel. And if you have a non-trivial kernel, that means that your inverse doesn't exist. Not too shabby. So typically, if we want unique solutions, we are looking for systems, square systems that don't have zero for an eigenvalue. Next proposition is what happens when you have complex eigenvalues. So specifically, if you are in a real matrix, right? If you have a matrix with real entries, then you must, if you have a complex eigenvalue, then you must also have that eigenvalue's conjugate for an eigenvalue. And the reason behind this is simply from algebra. So from the fundamental theorem of algebra, that your characteristic polynomial is a real polynomial. It's a polynomial in lambda with real coefficients, which means if this guy factors so that it has these, I guess you would have maybe a real factor, but if you had a complex factor, it would have to show up as an irreducible quadratic in the factorization. Right, so that means that you not only get lambda equals plus I, you would also get lambda equals minus I as a solution. Right, and this is just how real polynomials have to factor when you are not using, when you're not allowed to use, when you have real coefficients on that polynomial. So you see that in one way. Another way, you can just go ahead and have a look at what happens if you were to send A through this eigenvector V, and well, that would, because this guy is a real system, because this guy has because this matrix A is real, what you would have to do here, or what happens when you multiply A into V and take the conjugate, then you just have another real number, or you have another vector of real numbers, so it means that it's equal to its own conjugate. This vector is equal to its own conjugate. But if that's the case, then look what happens if we replace AV under the conjugate bar by lambda times V, because V is an eigenvector with lambda as an eigenvalue. Then the conjugate of a product is the product of the conjugates, and remember, V is a real vector here for all intents and purposes, which would mean that you would wind up with this for this lambda. Actually, what winds up happening here, I think, yeah, very, very technically here, I think this proof might not actually work, because V itself V itself necessarily has to be a complex vector. So what you actually wind up with is V bar here. I think you actually stop the proof right here, just to say that there is a, you actually use the fact that this is A times V conjugate. There we go. That actually makes more sense. So it's more to the point that the matrix is real, so that the conjugate bar only affects the eigenvector portion and not the matrix portion. But either way, however you'd like to see this, yeah, I'll have to retool the proof there, so I'll come back to it. But at the very least, proof 1 is correct, right? So if you have a complex eigenvalue, then you must also have its conjugate for an eigenvalue. Right, and I even have that down here as an example, this lambda squared plus 1 for the characteristic polynomial. Therefore, you have eigenvalues plus or minus I for this matrix, which actually corresponds to a rotation. And let's see. Yeah, if I were to compute the an eigenvector for this guy, or an eigenvector basis, yeah, see exactly what happens here, that this V, this basis vector that you would have to use, actually lives in C2. So this is actually a complex eigenvector. Yes, so as it turns out, not only are the eigenvalues conjugate to one another, but if you have an eigenvector for the original eigenvalue, then its conjugate is an eigenvector for the conjugate eigenvalue. So there's just this nice interplay between complex eigenvalues and their eigenvectors for real matrices. Now, it is always the case here. Oh, hey, I'm even saying that. Yeah, so proposition, this is always the case. Where, so if you have an eigenvector corresponding to lambda equals a plus bi, then a minus bi is also an eigenvalue, and the conjugate x minus iy is an associated eigenvector for that conjugate eigenvalue. Right, so again, nice interplay between complex conjugate pairs and the complex conjugate pair eigenvectors as well. Right, next, we need to remind ourselves that for a matrix, a square matrix with complex eigenvalues, so right, we're changing up the entries that can go in the matrix. So if we have a square complex matrix, then there is at least one eigenvalue, but no more than n of them. And again, this goes down to the fundamental theorem of algebra, that the determinant here, this characteristic polynomial, is an nth degree complex coefficient polynomial. So the theorem is really just restating the fundamental theorem of algebra, that this polynomial can be written as a whole, as a product of linear factors up to a multiplicity, right? And you include multiplicities, right? So we did this, let's say, for lambda to the fourth plus 2 lambda squared plus 1 is equal to 0. So we have a 4-dimensional matrix. This factors as lambda squared plus 1 squared. So it means I wind up with lambda equals plus or minus I. So that means that my characteristic polynomial would actually be, I could actually write the characteristic polynomial as lambda minus I squared times lambda plus I squared. And that's all this product is saying here. Right, this is a capital pi for product. So just like capital sigma is an S for sum, we have a capital pi for P, which is product. Okay, so this really is just a rehash of the fundamental theorem of algebra, that every polynomial can be factored into linear factors with linear factors as lambda minus a complex number to some power. And it turns out that this power is the algebraic multiplicity of the eigenvalue. So as a remark, it is possible to have geometric multiplicity 1 and algebraic multiplicity equal to n. We could basically fill up the entire matrix with one eigenvalue, but have the worst geometric multiplicity possible. And this is an object called a Jordan block. So it's lambdas down the diagonal and 1s down the super diagonal. And we can make these guys of any pairing, right? We can actually put as many Jordan blocks in here as we want in just an arbitrary matrix. Right, so not too worried about those in this case. But our next theorem then is that square matrices, square complex valued matrices, complex entry matrices, which again includes real entry matrices, and A transpose. So A and A transpose have the same characteristic polynomial, right? And you can actually see that pretty quickly here. If I go ahead and write this as, so the characteristic polynomial of A transpose is just going to be the determinant of A transpose minus lambda I. And that should be the same thing. So inside the parentheses here, this is exactly what I get if I just go ahead and transpose the I as well, right? I is the identity matrix is a symmetric matrix. It is equal to its own transpose. And, well, determinants of transposes are equal to determinants of the original object. So I can just go ahead and drop the transpose sign there so that the two characteristic polynomials are actually identical. So if I have the same characteristic polynomial, then I have exactly the same eigenvalues for these two matrices. The thing that's not necessarily the case is that I have the same eigenvectors. And we can be very explicit with that construction here. And I can show you that if I give you this A with that transpose, that these guys do have the same characteristic polynomial, right? So this will be just between the transpose and the original matrix, all I'm doing is swapping the 5 and the 3, or the 5 and the minus 3. So I definitely get the same characteristic polynomial. And if I set this guy equal to 0, I show that the linear factors are lambda plus 1 times lambda plus 3. So I'll get lambda equals minus 1 minus 3. So when lambda is equal to minus 1, I'll remind you that we can go ahead and pick up an eigenspace of E sub minus 1, which equals, the eigenspace is the span of the 1, 1 vector, and the eigenspace associated with negative 3 is the 3 by 5, span of the 3 by 5 vector. But if I carry out our computation for the kernel of A transpose minus, or A transpose minus negative 1i and A transpose minus negative 3i, I wind up with completely different eigenspaces. So do not be fooled here. You will get different eigenvectors for the same eigenvalues between A and A transpose. Okay, so you definitely get the same eigenvalues, but not necessarily the same eigenvectors. And the final theorem that you're going to have to remember from first semester is that the trace of a matrix, which is defined to be the sum of its eigenvalues, and the determinant of A is going to be the product of its eigenvalues. So specifically, the trace, remember, this is the sum down the diagonal of the matrix. Okay? And it turns out that this is going to be exactly the same as if we computed all the eigenvalues and then summed them together. So you can verify the characteristic polynomial for this matrix is negative 1 times lambda plus 1 squared times lambda minus 3. And I will have eigenvalues of negative 1. I'm going to have negative 1 twice here, right? I'm including the algebraic multiplicity for each eigenvalue. And I'm going to sum that with 3. So 1 plus minus 1 plus 1 is the same thing as negative 1 plus 3. So I get exactly the same sum of eigenvalues as I do sum down the diagonal, which I think is actually kind of a counterintuitive result. Like, why should summing some arbitrary elements of a matrix give you the sum of eigenvalues, something that's kind of invariant with respect to this matrix? It's weird, but it's true. And the same thing goes for the determinant. I can go ahead and compute the determinant of A by a cofactor expansion. That would be this line here. So I compute that determinant very quickly. And I find that it should be equal to negative 1 plus 2 plus 2. So I get a 3, which is the same thing as multiplying the eigenvalues with multiplicity all together. So I wind up with negative 1 squared times 3, which, sure enough, is actually the constant portion of the characteristic polynomial. Weird, but true. Right? So that's what you should remember, right? Facts that you should remember about from first semester linear algebra. Something that's not so familiar, something new. remember that we are trying to put this stuff into a computer. So finding eigenvalues and eigenvectors is a little bit different here, because we would be trying to find zeros of a polynomial, which numerically speaking isn't too difficult. But if we're going for accuracy and precision here, we can only store a finite amount. So no matter how we represent these eigenvalues in the computer, we are virtually guaranteed that we're going to misrepresent the exact values, which is bad, because even, so going back to our example here at the top, 2002, and the computer tells, oh, so I have eigenvalue lambda equals 2. If the computer represents that with some error, so lambda is approximately equal to 1.99, then I get a trivial kernel for this matrix. 2 minus lambda, 0, 0, 2 minus lambda is going to be some multiple of the identity matrix, and it's actually, what, 0.001, 0.001. And this guy has a trivial kernel, which is bad. I mean, there are only a finite number of exact numbers that correspond to the eigenvalues of this matrix, and the computer needs to get like right on those numbers. So actually computing a kernel here, like finding eigenvectors, is actually really difficult for a computer. So what we would like to do at the very least is get a good representation of the eigenvalues, because those guys we can compute as the zeros of a polynomial, right? Determinant of a minus lambda I. We can represent that in a computer fairly well. This would just be a function that we're trying to find the roots of. And there are many algorithms, Newton's method, bisection, there are many, or secant methods, there are many ways to find zeros of functions in a computer. It's a very common problem. So finding the eigenvalues is actually easier for us than finding the eigenvectors themselves. But we'll come back to how we can actually pick up the eigenvectors when we talk about iteration. That's actually a more reliable way of figuring these guys out. So we are, again, we're virtually guaranteed to misrepresent the eigenvalues, and therefore we are not going to be able to figure out the eigenvectors in our traditional sense. But we can know exactly how far away from the true eigenvalues the approximation for the eigenvalues actually are. And this is the new material. This is something that we probably, more than likely, haven't seen before. So let A be this matrix, minus 4, minus 2, by 4, by 5. So the eigenvalues, I can tell you, are located somewhere within the following regions of the complex plane. So I can actually go ahead and compute. The eigenvalues are, actually, if you wanted to go ahead and do this in MATLAB, which probably not a bad idea to know how to do that. So never mind the Lorentz polynomial, or the Lorentz butterfly going on in the background. That's for the dynamical systems class. You're welcome to go check out that playlist at any point. It's a really interesting class, and I have a blast teaching it. There we go. Let's go ahead and kill this off then, and go back to the command window. So we had a matrix, what, minus 4 by 4 by 4 by 5? Did I remember that correctly? Minus 4 by minus 2, 4 by 5. And then 4 by 5. So I can go ahead and throw this guy into the computer. The command that I want to use is eig. And this is going to give me a list of eigenvalues for A. Right? And I can go ahead and then compute the null space, A minus negative 3 times I, the 2 by 2 identity matrix I. And voila, I do indeed have a non-trivial kernel here, but that's because I chose very specific numbers for this matrix A. In general, this is going to be really hard for the computer to come up with any sort of accuracy. So then I can do minus 4 times the 2 by 2 identity matrix, and sure enough, I get a non-trivial kernel here as well. So I can go ahead and compute these guys in MATLAB, but if I were just going to do a random matrix here, random A matrix, so I don't know, maybe a 4 by 4 system. So A now is rand 4 by 4. I'm going to go ahead and compute null space, or I'm going to compute the eigenvalues of A. Right, so let's go ahead and make this list lambda equals eig of A. Come on. Fingers work. There we go. So those are my eigenvalues. Let's go ahead and do null space of A minus the first eigenvalue times the 4x4 identity matrix here. All right, so it looks pretty darn close. Okay, so we get really lucky with that amount of precision in the eigenvalue. But let's see, so format long. Let's have a look at how long lambda 1 is. Let's go ahead and create L equals 2.4. Oh, shoot, come on. You're killing me. No, I realize there are no suggestions. Get off. 402.116. 402.116. Let's just go ahead and do that. Oh, actually, we can keep on appending here. 7695, is that what I saw? 7695, and then 71058. So this is the entire eigenvector, or the entire eigenvalue. Let me just go ahead and shave off a few digits here. So let's go down to, what is that, 6 digits of precision, and try to compute the null space of A minus L times I, 4x4. It's empty, right? There is a trivial eigenspace, right? Because that's not an eigenvalue. It's an approximation of an eigenvalue. So if we are off, even by a fair, like a tiny amount here, right? We're off by what, less than 10 to the minus 7, or less than 10 to the minus 6. This is going to be a problem for us if we can't get a good approximation, or if our null space algorithm is not up to snuff. No, we're not going to cancel recording. We're going to go back to this example. So, going back to the original matrix, I showed you how to do this. We found eigenvalues of -3 and -4 for this original matrix up here, A. And indeed, for some reason, I chose these disks that live in the complex plane to say, I know where my eigenvalues have to be. So if I tell you that one of my eigenvalues has to live in this disk, sure enough, there's lambda equals -3. It lives in that disk. And for this disk, yeah, lambda equals 4, that lives in that disk. So how did I know that my eigenvalues had to live in these complex disks? The way that we're going to get these guys is that we are going to, for the first disk, grab the diagonal entry in the first row, and we are going to create the disk that has radius -2, or radius absolute value of -2, centered at x equals -4, or z equals -4. So I've created a disk of radius 2 centered at -4, 0, or the real number -4 in the complex plane. And very similarly, I'm going to go ahead and now go to the second row. The diagonal element here is the -5, and that's where my center is. And I'm going to go ahead and give this guy a radius of 4. So sure, it's a bigger circle or a bigger disk, but my eigenvalue is guaranteed to live in here. Why? That seems like such an arbitrary thing, but this is actually really useful to us, that we can go ahead and compute where the eigenvalues have to live in the complex plane based solely on the entries of that matrix. And this is beyond useful to us, especially for bounding arguments. So, the definition of what's called a Gershgorin disk. And let's see, technically that should be, I only just saw that, should be absolute values of A sub I k. If we have a complex entry matrix, we're going to define disks by being essentially how I describe them up here. We're going to take we're going to take we're going to take the center of each disk to be the diagonal element in each row, And then for each element, for each row, we're going to get the bounding radius by summing up the absolute values of the remaining entries in that row. And these disks are called Gershgorin disks. And the union is going to be called the Gershgorin domain for the matrix. And all eigenvalues for this guy must live somewhere in the Gershgorin domain, and that is a major theorem for us. We're not going to prove it, but I am going to exemplify it here, show you why that might be the case, or try to convince you. Okay, so once again, we're computing Gershgorin disks. So first row is going to correspond to the purple disk. We're centering that at 2 and giving it a radius of absolute value of 1 plus absolute value of 2. So that would be the disk centered at 2 with radius 3. That would be the big purple disk on the screen. Okay. Now we keep going. Second row, we're going to do that guy in red. We're going to say that we're centering this disk at -1, and we're going to give it a radius of 1 plus 1, so a radius of 2. That would be the red disk on the screen. And finally, the last row here, we're going to go to a blue disk and say we're centering it at 3, and we're going to give it a radius of 0 plus 2, which is 2. So the blue disk actually fits entirely inside of the purple disk. Sorry for my colorblind viewers. But let's see. The Gershgorin domain, D sub A, is just going to be the union of all these guys. So it's basically, if you turn your head sideways, it kind of looks like a two-snowball snowman, right? Because the blue disk is entirely contained inside the purple disk. So it's kind of like the snowman had a blue snowball snack, and it's just sitting there in his belly right now. But it does have a little, like a red head on top. So if I turn sideways here and do this in black, maybe he has this nice hat on top with little eyes and coal smiley face. But I digress. The Gershgorin domain is going to be that union of of disks, excuse me, not circles, definitely disks. Okay, and we can check the eigenvalues of this guy, right? We can run run some numerics on this. The eigenvalues, let's see, actually, let's go ahead and pull it up. I can do this right over here. So there's my A is going to be 2 by 1 by 2, 1 by -1 by 1, 0 by -2 by 3. There's A, and I can go ahead and compute I of A. And indeed, I can check that these guys, ooh, interesting. Did I enter that correctly? Looks like I did. Ooh, something interesting happened. I like it when interesting things happen. So I think that means my lecture notes might be incorrect here. Awesome, that means I can fix them right now. But we can still see, go ahead and look in here for what, -1.1.42, so -1.142 by 0, so that's roughly here. Yep, that's inside the Gershgorin domain. Then we're going to go to 2.571 plus and minus 1.1245. Remember, if I get one complex number, I get its complex conjugate for real matrices. So go to 2.5, and sure enough, I get the complex conjugate pair that sits inside the purple and the blue disks. So no problem. We actually wind up with exactly the correct thing now. So we do wind up with eigenvalues that live inside the Gershgorin domain. There we go. So these are incorrect, and I'm going to go ahead and fix those after the lecture here. And we can double check here. Oh, yeah, so it's just me being silly and thinking I didn't have an example that had complex eigenvalues. Nope, totally did. So this is showing yet another version of that theorem. And this is kind of a more traditional snowman without a snack. Okay, and the last thing I'll say about this guy is that, okay, so why would we care about these Gershgorin domains? Well, there's an easy application for us. If we have what's called a strictly diagonally dominant matrix, right, and feel free to think of that as just a matrix whose diagonal elements in each row are bigger than the absolute sum of the remaining elements. So the diagonal is definitely the tallest kid on the block. Like, it's bigger than all the other kids stacked on top of each other. So 3, 4, minus 1, minus 2 is not strictly diagonally dominant, but the original matrix we started with in the previous video, 4 by 1 by 1 by 4, is strictly diagonally dominant. And the theorem is that every strictly diagonally dominant matrix has an inverse. Right? It turns out the Gershgorin disks here don't have a radius that's big enough to contain the origin in the complex plane. So that means that we can't have a zero eigenvalue, which means that our matrix has to have an inverse. So don't worry too much about SDD matrices just yet. We'll come back to them if we have time in iterative schemes when we talk about the Jacobi and Gauss-Seidel iterations. But that will end this video. I know it's already really long, so let me just look real quick. Next thing that we're looking at is properties of eigenvectors and how we're going to use them in practice. So let's go ahead and kill this video. It's already way too long.